Hi. Our last video, we spent introducing the concept of vectors, and we had mentioned it before, but we hadn't really drawn any vectors. We hadn't really spent any time focusing on them. So last time, you learned what a vector is versus a scalar. You practiced drawing them. You practiced using your protractor a little bit, and you learned how to add vectors, I think head to tail. Yeah, you learned how to add vectors head to tail. The reason we're talking about vectors now is we're getting ready to move into kind of past like the definitions part of the kinematics unit to some applications where you might have to use vectors on occasion. So today what we're going to be talking about are what we call vector components. So let's start off with something that you did last time, adding two vectors together. Add the following vectors and draw and measure the resultant. Okay, so 6 centimeters at 0 degrees from the x-axis, for the positive x-axis, I just left that out, and then 4 centimeters at 90 degrees from the positive x-axis. So that's going to look something like this. Okay, so first one, 6 centimeters at 0 degrees. That's going to be pretty easy to draw. We just draw out, okay, to 6. Put the arrowhead on it. We'll put our new little compass rose. There we go. That's a little crooked. That's fine. And then 4 centimeters at 90 degrees, which basically means we're just going to draw more or less straight up. Okay, so we go here. There we go. And so the resultant is drawn from the beginning of the first vector at the origin to the end of the last vector. Put an arrowhead on that in a second. Looks like it's about 7.2, 7.3 centimeters or so. And for the angle, it appears to be, oh, I don't know, looks like about 33 or 34 degrees. So I would label this vector as maybe something like this, 7.25 centimeters at 34 degrees from the positive x-axis, okay? And you've just added those two vectors head to tail. Now, the reason I gave this example is this is a very special example because of the two vectors we were given. What's special about these two vectors? It should be obvious when you look at it. Look at them in relation to each other. They are perpendicular. And therefore, since they're perpendicular, realize what that makes for us. That makes a right triangle. The right angle is right here. Okay? We know this angle. We know this side is 7.25. We actually know the other two sides as well. But this makes a right triangle, and that's very important, okay? Because it means that we actually didn't even have to do all of this, and we still could have figured out the magnitude and direction of the resultant, the size and the angle from the positive x-axis. How could we have done that? Well, to find the magnitude, think about it this way. If we know that this makes a right triangle now, then we know that there's a special relationship with the sides of the right triangle as they relate to each other. You know it as Pythagorean theorem. Pythagorean theorem says a squared plus b squared equals c squared. If you take the two sides of the triangle, you square them and you add that together, and then take the square root of the result, you will get the length of the third side, the hypotenuse. So in this case, we had a side of 6 centimeters. We're going to square that, plus 4 centimeters, that was the side length of the other one. Square that, equals c squared. So let's see, 6 squared is 36. Plus 4 squared, which is 16, is 52. I take the square root, and I get c is equal to 7.21 centimeters. And if you look, that's very, very close to 7.25 that I got by drawing. Obviously, drawing is always going to introduce a little bit more uncertainty than a mathematical method, but it's really, really close. We can also find the direction. We can actually find out what this angle is just using math, knowing that these two vectors are perpendicular to one another and that we have a right triangle here. To find the direction, we have to use trig. Now, here was my angle, okay, this was 34 degrees, and this is the angle from the x-axis. That's very important. That's the angle we usually measure. If I'm using this angle, I can actually name all these different sides. for instance, this is the hypotenuse right here, the side opposite, or the side across from the right angle. This side is opposite the angle from the x-axis. It's the angle I want to use. It's the angle I want to measure. So this is the opposite side. And this is the adjacent side. So I now know the length of this side, the 7.21, 7.25 centimeters, whatever. Let's pretend I didn't even know that. All I had was the length of the opposite and adjacent sides. Trigonometry is the study or the measuring of angles and sides of right triangles, and there are certain trig functions or trig formulas that relate angles like this to these other sides. In particular, since we know the opposite side and the adjacent side here, I can use what is called tangent. So the way I write this is tan of theta, theta standing for angle, equals the opposite side over the adjacent side. And in this case, take a look at my opposite side. My opposite side is just in the y direction. Okay, imagine this is the y-axis, it's just in the y direction. My adjacent side is just in the x direction. So instead of writing opposite and adjacent in physics, a lot of times we'll just write y and x. We'll just use the names, okay, y and x. My y component is 4 centimeters, my x component is 6 centimeters. So this simplifies out to, like, you could write it as 2/3, you could write it as 0.66666, going on forever. But that's not our answer yet. That would be tangent of theta equals, okay, 4 over 6. That's not good enough. We just want theta. Theta is the actual angle. Tangent is a trig function, okay? It's a function. It's not like a variable. It's not like a number. In order to get rid of that function, we have to do the inverse function to both sides. What that'll do is it'll cancel out the tangent over here, and we then therefore write it like this. Theta, which is the angle that we're looking for, equals the inverse tangent, tan and the little -1 sign, of y over x. That's how we're going to find the angle. So in this case, it ends up being the inverse tangent of 4 centimeters over 6 centimeters. Now remember, this is a little button on your calculator. Whenever you're trying to solve for an angle, you will end up using the inverse of some trig function. If you're ever trying to find a side length, you just use the regular function. So what I do is I do 4 divided by 6. I get that. On this calculator, I'm going to hit second and then tan. That'll bring up tan -1. And it just pops up with the answer. The answer, the angle, ends up being 33.7 degrees, which again is very close to 34. So look at that. I predicted, or I calculated, the magnitude and direction of the resultant without actually doing anything, without actually drawing. I didn't have to draw. All I did was I knew that those two vectors would make a right angle, therefore I have a right triangle, and therefore I can use Pythagorean theorem and trigonometry. Okay, so that's really important. Basically what we're showing here is that you can add up two different vectors using trig, and I'll show that again a little bit later on. Now we know from the other day that the sum of two vectors is equal to the resultant. Okay, the other day we drew these vectors in here, we drew these vectors head to tail, then we drew in the resultant. The resultant is defined as the sum of those two vectors. But this also works in reverse. You can take any vector and you can break it up into its constituent components. Any vector can be written as the resultant of two perpendicular vectors that have been added together. We call these components, or component vectors. And I'll get more into what components actually are and how we draw them in just a second. But this is really important because the units we're about to move into, we're going to start dealing not just with one-dimensional motion, but two-dimensional motion. And for objects in two-dimensional motion, okay, objects that are moving in two different directions at once, perpendicular components of motion are independent. Perpendicular components of motion are independent. Now let me phrase that a different way. What happens in what we might call the x direction does not change what happens in the y direction, which is very interesting. Okay, we're going to get into basically the topic is called projectile motion. We're a little ways away from it, but I want to prep you for it now. In projectile motion, you have objects traveling not only horizontally, but vertically. Now, the horizontal motion does not affect the vertical motion, and the vertical motion does not affect the horizontal motion. So what happens sometimes is that you end up with these situations where certain components will affect some measurements, but not others. Different components may or may not have effects on certain measurements. And what we need to do is we need to separate vectors into components to be sure of their effects. Now, that's a lot of writing. I promise it will make more sense as we go into as we go and we start to demonstrate this. But first, we have to talk about these components. What exactly are they? How do we find them? Okay, so it says draw the following vector, 5.4 centimeters at 60 degrees from the x-axis. So as you remember, the first thing I'm going to do is get a bearing on the direction. 60 centimeters is about up there. I'm going to measure 5.4 centimeters in that direction. It's about there. Okay. Put an arrow on it. So we've drawn this. It is 5.4 centimeters. And when we have a vector like this, in Regents, they usually label like the thing you're going to break up into components A. I'm just going to call it R, okay, little lowercase r. And we know that this angle right here is that 60-degree angle. The x and y components of the vector we're going to draw in now. So here's the definition. The x component of a vector, or the x component of some resultant or some vector, is the original vector's extent in the x direction. That's all it is. It's how far the original vector goes in the x direction. You can see that very easily by just kind of line this up with the vector. Well, and you'd say, okay, well, this vector very clearly goes out to about here. Yeah, that's the x component. That's literally the x component. We would draw that by doing something like, well, here, let me make a mark. Okay, that goes up to about there. Now, we would draw this vector by doing this. Okay, so we draw these components out sometimes. Okay, and this one we're definitely going to use dashed lines for, or dotted lines, whatever your preference is, just not solid. Okay, that right there is the x component. The y component is the exact same thing, but obviously in the y direction. In the y direction. So one thing to be careful with is don't get freaked out if you see the y vector or the y component drawn a little bit differently. I'm going to draw mine like this. Okay, but don't get freaked out if you see it over here or you see the x component up here. Remember, since they're this is still going to be horizontal, this is still going to be vertical, they're going to be the exact same size, but you might see them drawn slightly differently. I'm going to measure both of these. This x component, okay, yeah, I might have messed up drawing this just a little bit. Looks like about 2.5 or so. This y component, let's see here, start there. Yeah, I'm not drawing this. I didn't draw this super well. But that looks, actually that one looks pretty good. That one looks like it extends up to about 4.6. And again, I'm just going to label this. This is the y component, and this is the x component. So This time we drew in the x and y components. We started with a vector, and then we broke that down into its x and y components. Before, we had on the front, even if we didn't mention it, we had the x and y components. We made a resultant out of that. Now we're doing the opposite. We're taking a result and breaking it down into components. Now, we measure these components. Obviously, this isn't just the x direction. This is the extent of the vector just in the y direction. You don't actually have to draw these and measure them to figure out the lengths, the sizes, the magnitudes of the x and y components. You can figure this out by using trig. Here's how you do that. We have an angle, and we know this side length. We know r. We know the hypotenuse because that's the original vector. If we want to find x or y, we can use trig to do that. X, we would say, is the adjacent side. It's the side directly next to that angle. Here's my right angle, by the way. But this is the angle that was measured from the x-axis, so this is the important one. This is the opposite side, so I'm just going to write opposite and adjacent. You know the two trig functions that have to deal with comparing adjacent sides to the hypotenuse and the opposite side to the hypotenuse. If we're looking for the x component, then we're going to use, let's see, we want to know the adjacent side. Okay, we want to know the x component. We have the hypotenuse and we have this angle. Adjacent and hypotenuse, that's cosine. So what we would write is cosine of theta equals adjacent over hypotenuse. Or, as we would write in physics, okay, we're not going to use this much, but this is what you're familiar with from math, the x component over the hypotenuse, which I'm just calling r here. And actually, we don't even write it like this in physics. We rearrange this into a different formula. We rearrange this to solve directly for the x component. Basically, what that means is multiply both sides by r. You end up with this. X equals r cosine theta. To find the x component, you take the hypotenuse, you multiply by the cosine of the angle that that vector is at from the positive x-axis. So let's do that. X equals 5.4 centimeters times the cosine of 60 degrees. On this calculator, I type in 60, hit cosine, times 5.4, and I get 2.7 centimeters, okay? Components always have the same units as the parent vectors. So I said 2.5 over here. I must have mismeasured just a little bit. That's fine. X is 2.7 centimeters. That's the size of the x component. Very, very close. To find the y, that's the opposite side. Pretend I don't know the adjacent side yet. Well, I have the hypotenuse, I have the angle, I want to know the opposite side. Opposite and hypotenuse, that's going to be sine. Sine of theta equals opposite over hypotenuse. Or, in our case, y over r. And we're going to do the same thing. We're going to rearrange to solve for y. So we're going to have y equals r sine theta. So you see the pattern. To find the x component, take the original vector's magnitude, multiply by the cosine of the angle, or cosine of the direction. To find the y component, same thing, except instead of cosine, it's sine. Y equals 5.4 centimeters times the sine of 60 degrees. Y ends up being about 4.68 centimeters. Again, very close to my drawing estimate of 4.6. Drawing, again, is never going to be as accurate as actually measuring. So what we've seen here is that you can use trig in order to find x and y components. And I do just want to make one quick note. These formulas only work if the angle theta is measured from the positive x-axis. That's the only time that they work. The last thing I want to show you in this video is how to add vectors without actually doing all the head to tail stuff. You're going to add them just using trigonometry. Okay? And actually, I suppose there is a step 0. This is the same exact example you saw in the last video. Yeah, these are the same exact vectors that you saw in the last video. The first, so we want to figure out the resultant just using trig. I said no drawing, no head to tail stuff, but step 0, I guess, is we are actually going to make a sketch. make a sketch of what this should approximately look like. Okay, here's our axis. Our first vector, 6 centimeters at 125 degrees from the positive x-axis. That's going to be quadrant 2. It's going to be, I don't know, something like this. And then 9.4 at 332 degrees from the positive x-axis should be a longer vector and should be in quadrant 4. So probably something that looks about like this. So the resultant should be, I don't know, somewhere in quadrant 1, maybe quadrant 4, but somewhere about like that, and should probably have a bigger x component than a y component. Should be, more horizontal than vertical. So that's step 1. That's just to ensure that we're on the right track and we don't get anything way out in left field. Or that's step 0, I should say. The actual step 1 is break the vectors, every vector that you have, into x and y components. Now, we're going to do that over here. So here's for vector 1. We find the x components for vector 1, the x component, or x and y component for vector 1. X is r cosine theta, r being the length of the original vector, theta being the direction or the angle, and y equals r sine theta. 6 centimeters, so for the first vector, it's 6 centimeters at 125 degrees. So we do 6 centimeters times the cosine of 125 degrees. For y, we do 6 centimeters times the sine of 125 degrees. 125 cosine times 6. Oh, make sure you're in degrees for this. You can't be in radians. So you might get a negative answer. That's fine. Think about this. For the x component for vector number 1, we got that the x component is negative 3.44 centimeters. Think about what that means. That vector is in quadrant 2. Of course its x component is negative. That's where the x component should be negative. It makes sense. It's going backwards. It's going in the negative x direction. Okay, that's the direction that the x component points in. This one, however, the y component for a vector number 2 in quadrant 2 should be positive. 125 times sine times 6 gives us a y component of 4.91 centimeters. What about for vector 2? X equals r cos theta, y equals r sine theta. But this time there's a different magnitude of the original vector and a different angle, so we're going to get different numbers. X equals 9.4 centimeters times cosine of 332 degrees. And it doesn't matter if you feel weird typing in a number like 332, that's what you should be doing. You always use, these formulas only work if the angle is measured from the positive x-axis. That's why I have to include that. So cosine of 332 times 9.4 gives us 8.30 centimeters. And the y component is 9.4 centimeters times the sine of 332 degrees. And the y component is negative 4.41 centimeters. Okay, so we've split both vectors up into their x and y components. Step number 2. Add the x's together and add the y's together. So we're going to have a total x component, negative 3.44 centimeters plus 8.30 centimeters. I'm just going to do xt plus 8.30 is 4.86 centimeters. And the total y component, that would be 4.91 centimeters minus 4.41. We have to make sure that we understand that that's minus. You can't just go around taking the minus off. It's in the negative y direction. We have to account for that. Yt equals 0.5 centimeters. So we've got the total x and the total y. our next step is to use the Pythagorean theorem to find the resultant's magnitude. As we remember, Pythagorean theorem is simply a squared plus b squared equals c squared. The a squared and b squared, this is the total x component. So think about it. This is the total extent of this new vector in the x component. Okay? We've added together the x's of both of these original vectors, and now we have the extent of the new vector, the resultant, in just the x direction. This is the same thing, but in the y direction. Those have to be perpendicular to each other. If we want to find the resultant is just the side that connects those two if those two are added head to tail. So 4.86 centimeters squared plus 0.5 centimeters squared equals c squared. 4.86 squared plus 0.5 squared. Take the square root. We get 4.89 centimeters is the length of the resultant. In step number 4, we use the inverse tangent, just like before, to find the direction. We've got the magnitude, we've got the size of the resultant vector, that's right there. We're going to use inverse tangent of the y component over the x component to find the direction. Okay, so right now, we imagine it like this. We've got this x component, we've got this y component, the total x, total y. We can find the resultant by using Pythagorean theorem. We can find, or the magnitude of the resultant by using Pythagorean theorem. We can find the direction by using inverse tangent. And I should point out there is one little thing that you have to be careful with here. If your total x component is negative, then what you have to do is you'll get a really weird answer for your angle. What you have to do is you have to add 180 degrees. But that's only if your total x component is negative. And I'll write that down in just a second. Okay, 0.5 divided by 4.86. Take the inverse tangent. We get an angle of 5.87 degrees. Okay, so just put a little note. If xt is negative, add 180 degrees to theta once it's calculated. There's a reason why we do that. It goes into how the calculator itself works. Basically, if your x component is negative, the calculator doesn't realize that you need the x component to be negative. It'll put the negative on the y component instead, and it just messes everything up. To fix it, you add 180 only to this, and that's only if the total x component is negative. It's not, so we don't have to worry about it. Finally, we get our final answer. The resultant, this vector, we would label it like this. The resultant is 4.89 centimeters at 5.87 degrees from the positive x-axis. You can go back and check from the last set of notes that this is almost exactly what we drew. This is actually a more accurate answer, but it's very, very close to what we drew. And our predictions came true. It's in quadrant 1, the x component is bigger than the y component, etc., etc. The focus of these notes has been to get you comfortable using vectors and vector components. It is something that you will have to do for the rest of the year. You will be using sine and cosine. And in a few weeks, it'll be completely second nature to you. But it is something that is a little intimidating at first, which is why we did a separate note video for this, just for vectors and components. We're going to be moving into the last part of our freefall unit, or excuse me, our kinematics unit now. We're going to talk about freefall, and then we'll talk about projectile motion. Talk to you later.